So we've just gone through a lot of setup to get to this point. So we have already done confidence intervals, and now we've looked at sort of the setup that we need to take to make a null and alternative hypothesis. We've looked at how you make decisions using the critical value approach and also the p-value approach. And now it is time that we can move forward with hypothesis testing. So the first hypothesis testing procedure that we're going to talk about is the one population mean when your standard deviation is known, and this is our one mean z-test, or just simply the z-test. And here is that procedure for it. So the purpose is to perform a hypothesis test for the population mean. Our checklist of things we need to have is that it needs to be a simple random sample. It needs to have a normal population or a large sample size, and we need to know the standard deviation. Now, our first step in this is going to be determining our null and alternative hypothesis. So for this course, our null hypothesis is always going to be no change. HO mu is equal to mu sub O, and then our alternative hypothesis will be based on the question, whether it becomes two-tailed, left-tailed, or right-tailed. And left-tailed, they are indicating it is less than, right-tailed, they're indicating it is more than, and then two-tailed is indicating it's just different from. Then we will decide on our significance level alpha. It's given to you in the question most of the time. If you don't get it though, in a question, then just assume 0.05. Compute the value of the test statistic, and this is the formula here. You've already seen this, and of course this is also located on your formula card. And then after you get this test statistic, you need to make a decision about your null and alternative hypothesis, and you can use either approach, the critical value approach here, or you can use the p-value approach, which we went through. So let's do some practice. Before we get into the practice, though, I did want to mention when we can use the one mean z-test in terms of sample size. So a small sample is less than 15, and unless it's very normal in its distribution, you shouldn't use it. And then a large sample size is going to be 30 or more, and then you can use a z-test without restriction. 15 to 30 is a moderate, and a z-test can be used as long as you don't have a ton of outliers in there. All right, in this question here, we're looking at, again, the height of young women and how that's changed over time. So you can see that we've got a table. This is the height in inches of a random sample of 25 of today's women in their 20s. And the question is asking us, at the 1% significance level, do the data provide sufficient evidence to conclude that the mean height of today's women in their 20s is greater than the mean height of women in their 20s half a century ago. Assume a population standard deviation of heights for today's women to be 2.88 inches. Okay, so our null hypothesis here is that the mean is going to be the same. No change, no change, no change. Mu is going to be equal to 62.6 inches tall, which is given to us here. Now, it's asking us, though, if the height of today's women is greater than. So we are doing a right-tailed test. Is it greater than the 0 or the 62.6 inches today? And so that's the hypothesis test that we're going to be, or the hypothesis we're testing. All right, so the first step is, of course, going through all of the checklist of things we need to make sure that we can do this test. It's a simple random sample. We're just going to go forward and say it is because in the example in the they said a random sample. And then we have to check for normality, and you can see that that was done here doing a QQ plot, and you could also do your Shapiro-Wilk as well. And then we actually just perform the test itself. So we pop all of the information we have into this, and then we're going to perform this again at alpha equals 0.01. So let's see what happens here. And before you even move on, you should try to do this and calculate Z to see if you've done it right. All right, so we put all of the information we needed to inside this table here. So we've got 62.6 as the mean that was given to us, but where did this 64.24 come from, do you think? Well, if you look at the equation, it's x bar, so you just have to calculate the mean of these here over the standard deviation of 2.88, which was given to us, divided by the square root of 25. Now we're going to use the critical value approach in this one here. And so we have an alpha at this time of 0.01. So make sure that you grab out your table so that you can look up this value as well. So you take 1 minus 0.01, look in the body of the table, and then you will match it up and you will find 2.33 is your critical value. And so if you draw it on here on a number line, you put 2.33 here, and our test statistic is 2.85. So it's way, way out here in the rejection region, and so we reject HO. Okay, but what about the p-value approach here? So we're going to use that 2.85 as our z-score, and then we'll find the area, which is 0.9978. And you can just look in your table and you'll find that. But then I'm going to take 1 minus 0.9978. Why? Because it's the area to the right. So do you remember when we were doing all this work on normal distribution? It was always 1 minus when it was the area to the right. And so 0.0022 is going to be our p-value. But now we want to compare our 0.0022 to our alpha level of 0.01. And the p-value of 0.0022 is less than the significance of 0.01. So again, we reject HO. So one thing I want to mention is that statistical significance does not necessarily imply a practical significance. So significance only really means that the data provides sufficient evidence to conclude that the truth is different than the stated null hypothesis. And I have an example for you. When my sister, this was years ago now, 13 to be exact, when my sister was in labor with my niece, being the dutiful little sister that I am, I was timing her contractions, and I love data. So I started to collect the timing of her contractions, the strength, and all of this in an Excel file in the hospital. I'm not even kidding. And so what I ended up doing was I used the timing of her contractions to model when I would, when I think the baby would be born. And so when I did all of this statistical work, I ended up with a p-value that was 0.07 or something along those lines. So it wasn't statistically significant, but biologically it was pretty significant if you think about the timing of a baby. So when my niece was born, she was born at about 7:30 in the morning, and I had predicted that she would be born around 6:45 in the morning. So it might not have had a statistical significance, but it was very practically significant. So over the years teaching statistics, and I have to say, I haven't taught this course online for many, many years. It's been since COVID, really, that I've done this. So anyways, I apologize if the videos kind of aren't as the best quality. I'll work on it, I promise. But anyways, so one of the things I've noticed is that sometimes my students get very confused about hypothesis tests versus when they're doing a confidence interval. So there will be a confidence interval that is paired up to every single hypothesis test that you have. But I've got this little chart here that was it was kind of like automatically generated on like an AI thing, but it works. It's okay. So keep in mind that the output of the hypothesis test is a p-value, and you can reject or fail to reject a decision. Not always a p-value. In your case, you'll have critical values, whereas the confidence interval is giving you a range of values. It's giving you those bookends, the lower bound versus the upper bound. Now, the focus of your hypothesis test is to test a specific claim or theory. Usually we're looking at a mean or a standard deviation, whereas the confidence interval is estimating the magnitude of an effect. It's estimating the range, right? And the question would be, is there an effect versus how large is the effect? And the practicality, the hypothesis test will tell you if a result is real or just noise, and then the confidence interval provides context on the precision of the estimate. All right, so we've already done the confidence interval for the Z. We've also done the hypothesis test for the Z, but now we can do hypothesis tests for one population mean when we don't know the standard deviation. And you guys have already done the confidence interval procedure that goes with this. This is the formula for the one mean t-test. And so in real life, the population standard deviation is often not known. We don't really have that information. So we'll use the t-test in those cases. And you can look on your formula card and the formula is there for you, but it's also written out here. T is equal to x bar minus mu over s divided by the square root of n. And what changes in here is that we're using an estimated standard deviation, a sample standard deviation, rather than being able to use the population standard deviation. And the final thing that I want you to note in here is that we've got n minus 1 degrees of freedom. And as you start looking more at your formula card, you will see that lots of the tests have different degrees of freedom that they require. And again, the degrees of freedom really, it stands for like the currency, it's the cost you need to pay in order to run a test. And so if you have no degrees of freedom, you can't run the test. You don't have enough currency to do that thing. Okay, so the p-value for t-tests, it's a little bit different. And again, we'll do some practice on it so that you get used to it and you understand it pretty well. So if the null hypothesis is true, the test statistic for a t-test has a t-distribution with a df of, or degrees of freedom of, n minus 1. Probabilities equal areas under the t-curve, and you can determine the p-values as shown below, and it's similar to our z-values. But unfortunately, using our tables, we can only estimate our p-values. We can't actually get a full p-value from a t-table. So for this section, you're going to want to pull out table 4, which is your t-table. And I've got like a little copy of it off to the side here. And I'm going to show you guys how to estimate the p-value for a one mean t-test. And it is kind of odd, but just stick with me on it. So we've got here a left-tailed test, n is equal to 12, and our t-value is equal to negative 1.938. So a t-curve is symmetric about 0, so the area of the left equals the area to the right. So it doesn't really matter that this is a negative. We're just going to pretend it's a positive. So what we're going to do is we are going to estimate our p-value. So what you do is you go with your df. So we have an n of 12. df is n minus 1, so df of 11. And you go into the row 11, okay? And you try to find the number that is most close to your value, 1.938. So in 11, you can see that 1.938 falls in between this 1.796 and 2.201. It's somewhere in between here. It straddles that line. So what you do to estimate your p-value is you go in between those two and you go up. Otherwise, you just choose the one that it's closest to. And your p-value is going to be between 0.05 and 0.025. So it's going to be greater than 0.025 but less than 0.05. And that's how you estimate your p-value. Okay, let's try this one now. This one here is a two-tailed test, and the p-value is the area under the t-curve with a df of 25 minus 1, so 24. And again, we know that it is symmetric about 0, so even though we have a negative 0.895, we can just call it 0.895 and it won't matter. So let's look in row 24. And we're going to look for the number that is closest to 0.895. And what you'll find is that none of them are. It's way below even this one. So in other words, what you will end up saying is that it is less than 0.10. Okay, so now this is the procedure for the one mean t-test, and if you look at it, it's doing all the same things as the z-test, except for we don't have our standard deviation anymore. The other thing about the t-test in particular is that it's really robust to moderate violations of normality, and it's really robust to even things like outliers. But of course, if you have a small sample size, you want to make sure that you get a bigger sample size. So this is the procedure. All of this stuff, remains the same. So we've got, to use your critical value approach versus your p-value approach. And of course, now with the t-table, you do have to estimate your p-value in that kind of odd way. I really like this example because it kind of plays into my background in environmental sciences and as a professional biologist, but I try to keep things a little bit more in the healthcare field for you guys, but hopefully you can stick with me on this one. So this one here is acid rain and lake acidity. So acid rain from the burning of fossil fuels has caused many of the lakes around the world to become acidic. True story. And so in this one here, they're asking us to, do the data provide sufficient evidence to conclude that on average, high mountain lakes in the Southern Alps are non-acidic. And so what is acidic? Of course, anything below 7 is acidic, with 7 being our neutral. And they're asking us to do a right-tailed test. And that they're saying here that the high mountain lakes are not acidic. So you take all of the data here and we're going to see if it's normal. So run a QQ plot, or of course you could do your Shapiro-Wilk. We now have our null and alternative hypothesis, and we're going to perform this test at the 5% significance level. And here you go. Here is the formula for it. So in this case, you're going to have to add all of these together and then divide it by 15 to get your X bar, your mean. And then you'll actually have to calculate your own sample standard deviation as well. Okay, so all we have to do is pop all of our pieces into that formula here. So we've got X bar of 6.6 minus 6, which was the mean that they gave to us here, over our standard deviation, which is calculated out to be 0.672 divided by the square root of 15, and we get a t statistic of 3.458. But that doesn't tell us if we're going to reject our null hypothesis or fail to reject it. So first, let's start with the critical value approach. Now we've got a DF of n minus 1, which means 15. There were 15 lakes. Minus 1 is 14, and an alpha of 0.05. Now to find your critical value, you're going to get your table 4 again, which is your t-table. And what you want to do is you want to look for down the left column side for your DF of 14. And then along the very, very top, your alpha is 0.05. So you just match up the 14 with the t 0.05, and you'll get the critical value here of 1.761. So again, number line it, put your critical point here. Our number is 3.4, so it's going to be over here. It's going to be way higher up on this number line here. And so we reject our HO because it falls within the rejection region. And we can say that the test results are statistically significant at the 5% level. Now we want to do the same thing, but we want to do it estimating our p-value. So again, we're going to get our table for our t-table, and we've got a DF of n minus 1, which is again 14. So I'm going to look for 14, and then in the table, I'm going to look for the number that is closest to my 3.458. And if you look at the table here, the highest number that it goes up to is 2.977. So it is actually less than 0.005. And so the p-value is less than the specified significance level of 0.05. So we reject our HO and state that the test results are statistically significant at the 5% level.